SwayamPrabha. Digital India. Educated India.
So, this will be lecture number 37 on mechanical measurements. Towards the end of the last lecture, we were looking at the measurement of thermal conductivity by the use of a radial heat flow apparatus, and what we will do in this lecture is to start with an example based on data taken from a thermal conductivity apparatus which is in the radial heat flow method. This will be followed by a discussion on thermal conductivity comparator and an example 43, and then we will look at a transient technique, the laser flash method, which actually measures directly not the thermal conductivity but the thermal diffusivity, and then we will say how thermal conductivity can be estimated from that measurement. Once we have completed a discussion on thermal conductivity measurement, we will move on to the measurement of heat capacity, and we will, of course, if time permitting, we will take an example on that as well. So, the example number 42 is considering the data taken from a radial flow apparatus, and the delta, the gap between the inner cylindrical plug which is heated and the outer annular cylinder across which the heat is going to be transferred through a sample which is kept in that gap has a thickness of 0.3 millimeters, a very narrow gap between the inner and the outer cylinders. The heat flow area has been measured by measuring the diameter of the plug and the length accurately, and it is given as 0.0133 square meters. And the data actually was corresponds to an experiment that was performed with unused engine oil. The engine oil itself is characterized by SAE number 40, and it is taken from the can directly, a new can which is opened and directly taken, not used earlier. The experiment was conducted by supplying a heater voltage of 40 volts, and the heater has a resistance of 53.5 ohm, which is measured accurately. Actually, in this particular case, the manufacturer of the equipment specifies the voltage, specifies the resistance of the cartridge heater. The plug temperature is measured and the jacket temperature is also measured, and the two measurements are given 32.9 for the plug temperature and the jacket temperature is 28.2. So, you see that the difference in temperature between these two is the driving potential for the heat transfer. So, we are asked to find out the thermal conductivity of this oil sample, and also we would like to find out what is the errors in the measurement. We are interested in finding out what is the error bar on the thermal conductivity, given that the following uncertainties in the estimated values of in the values which are measured are given. Delta V, the voltage is measured with plus or minus 0.5 volts, which may be improved with a better apparatus, but in this case it is plus minus 0.5 volts, and delta T is known to be within plus minus 0.2 degrees Celsius. We also are given that a separate experiment has been performed to determine the heat loss as a function of the temperature difference between the plug and the jacket. If you remember, towards the end of the last lecture, I said that we can determine the heat loss as a function of the temperature difference by performing an experiment with a medium whose thermal conductivity has been or is known very accurately. So, one easy way of doing that is to perform the experiment with air within the narrow gap between the inner and the outer cylinder, and we know the thermal conductivity of air. Therefore, for different values of the temperature difference between the plug and the jacket, we can actually estimate the heat loss by assuming that the thermal conductivity of the medium is known accurately. So, an experiment of that type has been performed, and the loss has been indicated as a function of theta. In fact, toward the end of the lecture I mentioned this expression. It is given by a cubic in this particular case, and the theta can be anywhere between 2 degrees and about half a degree and 10 degrees. That is the validity of this expression. So, with this data, let us work out the solution to the problem of determination of thermal conductivity as well as the estimation of the error in the measured value of the thermal conductivity on the board. So, let me just write down first of all the data which is given. So, we are given the voltage supplied to the heater is 40 volts plus or minus 0.5. This will be the error bar. I am combining it here. We are also given that delta T is nothing but the plug temperature minus the jacket temperatures, and these two are given 32.9 minus 28.2. These are the two measured values. This will give you 4.7 degrees Celsius, and each of the temperatures has got a plus or minus 0.2 degrees Celsius uncertainty. This is also specified in the problem. And the expression for the loss I can write down now, which is a function of theta, which is nothing but this is nothing but your theta in that expression. All I have to do is to substitute this into that expression, and I will get 0.0511 plus 0.206 into 4.7 plus 0.0118 into 4.7 squared minus 0.000153 into 4.7 whole cubed, and this comes to 1.26 watts. The heat loss because of the temperature difference equal to 4.7 degrees between the plug and the jacket is 1.26 watts. Now, we will calculate the heat supplied to the heater. Heat supplied under the steady state, of course, this amount of heat supplied has to flow through the specimen oil sample, or some of it is of course lost from parasitic losses through other channels, and therefore, the heat transfer through the sample is the difference between the heat supplied and the loss. So, heat supplied can be calculated as the power, electric power is given by V squared by R. This will be 40 square divided by the resistance of 53.5 ohms. This gives you 29.91 watts. So, we can say that the heat transferred through the oil sample which will be the difference between P and L. This will be 29.91 minus 1.26, that gives you 28.65 watts. So, we have the heat transfer to the through the oil sample, and we can now calculate the thermal conductivity of the oil. So, if you look at the thermal conductivity of the oil, the Q passing through the oil, Q transferred through the oil must be equal to K of the oil multiplied by the area for heat flow multiplied by theta, the temperature difference, divided by delta. Because delta is very small compared to the diameter of the plug, we can use this is nothing but the slab formula. We are using the slab formula because the thickness of the oil film is very small compared to the diameter of the plug, and therefore, it is almost like a planar slab. Therefore, I can say K of oil is equal to Q divided by A multiplied by delta by theta, and all I have to do is to substitute all the values. This will be 28.65 multiplied by delta is 0.3 into 10 to the power of minus 3. It is given in millimeters, so I have to convert it to meters. So, it will be 10 to the power of minus 3 divided by 0.0133 square meters is the area available for the heat flow multiplied by 4.7 degrees Celsius. So, this will work out to 0.137 watts per meter degree Celsius. This is the first answer we require. The thermal conductivity engine oil is 0.137 watts per meter degrees Celsius. The second part of the problem requires a calculation of the various uncertainties and the effect of these uncertainties on the value of K, which is determined here. So, for that, what we have to do is we have to do an error estimate using error propagation theory, which we already have talked about earlier in one of the earlier lectures. And you also see that the error is because of error in whatever quantities are specified, and uncertainty only we will take into account. For example, error in area is not taken into account, delta we are not going to take into account. These we are going to assume to be highly accurate, so that the error is not going to be due to any of these things. Error in those quantities which have uncertainty specified in the problem. So, we can do that one by one. For example, if you take theta, it is the difference between Tp and Tj. Each one is individually having plus or minus 0.2 degrees Celsius, and you will immediately see that delta theta or the error in theta is nothing but square root of 2 times the error in any one of the temperatures. This can be verified easily, and therefore, this will be plus or minus root 2 into 0.2 degrees Celsius, and that comes to 0.283 degree Celsius. This is the error expected in the value of delta theta, because each of the temperatures measured is prone to an error. The error in delta theta is, the theta is now equal to square root of 2 times the error in one of the each of the individual temperature measurements. We also know that Q is equal to P minus L, and this has got a plus or minus 5% specification. P has an error because we have an error in the value of the voltage which is measured. We are again assuming that the resistance has no error specified on that one. So, we have Q equal to V squared by R minus L, and therefore, I can find out the partial derivatives, and dou Q by dou L is equal to minus 1. Now, I can use the error propagation formula, substitute the values of the voltage and the resistance, and therefore, delta Q is equal to plus or minus square root of, we are going to use the error propagation formula, whole squared, and we can put it here. Dou Q by dou V is 2V by R, 2 into 40 by 53.5, delta V is 0.5 whole squared, plus dou Q by dou L is minus 1 into delta L is 5%. That means that we have to put it as 5 by 100 into 1.26, which is the value we identified earlier as the loss. This gives you plus or minus 0.75 watts. There is an error, or there is an uncertainty of the measured value of the heat transfer through the sample of plus or minus 0.75 watts because of the error in the measured voltage as well as the error in the estimated value of the heat loss from the system. So, now I think we have all the things which are required to determine the error in K. So, we can just go back to the expression and see K of oil is Q passing through oil divided by the area of available for heat flow multiplied by delta divided by theta. A and delta do not have any error in them. Therefore, all I have to do is to, this is also in the form of a product of quantities divided by product of quantities. So, I can use the logarithmic differentiation, which you remember we have done earlier, and therefore, delta K, I will drop the subscript. We know we are talking only about the K of oil. Delta K by K is equal to plus or minus square root of delta Q by Q whole squared plus delta theta by theta whole squared. And we have determined all the quantities earlier. So, this will be plus or minus square root of delta Q is 0.75 divided by 28.65, which is the estimated value of Q, plus delta theta by theta is 0.283 divided by 4.7 whole squared. This will give you, if you want you can multiply by 100 to get the percentage value. So, this will be 6.6%. We can now write the answer as the K oil equal to 0.137, which was determined earlier, plus minus 6.6% of this value, which works out to 0.009, so many watts per meter degrees Celsius. Just to recapitulate what we have done in evaluating the error bar or the uncertainty of the thermal conductivity of the oil, we have taken into account the errors or the uncertainties specified in the value of q and theta, and the all other values have been assumed to have no uncertainties because they are not specified in the problem. Let us look at the loss term, which is given as a function of theta, and you can see that I have plotted the function loss versus the theta, which was the function given, cubic expression which was given, and in the specific problem we have considered the temperature difference is 4.7 and the corresponding value of the loss is 1.26, and if you remember, the value of delta q, the uncertainty in the value of measured q is about 0.75 watts plus or minus 0.75, and you can see that the loss here is even larger than the uncertainty which we have specified, which you have got in the problem. Therefore, it is essential that the loss, which is about 1.26 watt in this particular case, is taken into account, because if you do not do that, you will incur a very large error in the value of k which is determined, even though the k itself has got an error of about 6.6% because of the uncertainties in the quantities that are measured. And of course, that includes also the uncertainty in the loss, because when you calculate the uncertainty, you have taken into account the uncertainty in loss also we have taken into account. So, with this we will take a look at another way of measuring thermal conductivity using what is called the thermal conductivity comparator, and it is very useful when you have the sample available in the form of rods, cylindrical specimens are available, and if you have a standard reference material SRM, which stands for standard reference material, whose thermal conductivity has been documented extensively and available in the literature, then we can take that standard reference material as one of the materials and prepare, as shown in this particular figure, take a specimen B of material whose thermal conductivity is not known, same diameter as the standard reference material, put them together, stack them like this, one above the other, insulate on the lateral side so that there is no heat loss from the lateral direction, and you subject it to a temperature difference, high temperature at the top and the low temperature at the bottom. Now, what we are doing by this thermal conductivity comparator is to place the two materials, the standard reference material whose thermal conductivity is known and the material whose thermal conductivity is to be determined, in series, and the heat transfer which occurs through the standard reference material is exactly the same as the heat transfer that takes place through the material whose thermal conductivity is to be determined. So, the common factor in these two, in the case of the standard reference material and the thermal material B, is that the same amount of heat is transferred through the sample as well as the standard reference material, assuming that there are no losses in the lateral direction. In fact, instead of insulation, we can in fact use vacuum as a possible choice, because vacuum will give you a good insulation, and of course, the vacuum chamber or the walls of the chamber can be maintained at a temperature which is close to the temperatures of these two media here. These two samples, sample and the reference material, if you can maintain a small difference in temperature between these two and the walls of the vacuum chamber, the heat loss from the lateral direction can be reduced to a significant extent, and therefore, whatever heat transfer takes place through the SRM also takes place through this. So, the common factor is the heat transfer, which is the same in the two cases, and we invoke the Fourier law, and by measuring the temperatures at these 4 points as indicated here, these are the thermocouple junctions. The distance between the first two thermocouples in the SRM is LA, and in the case of the material of unknown thermal conductivity is LB. LA and LB are accurately known, and of course, I have shown these thermocouple junctions to be very big. In practice, they are going to be very thin junctions, very small junctions. They may not be embedded inside the solid, it may be at the surface if necessary. It is easier to attach at the surface and measure the temperature. You need not drill a hole, otherwise you will have to do that, and of course drilling a hole will probably change the heat transfer pattern slightly. So, that is also not a very desirable thing. So, what we do in this thermal conductivity comparator is to measure the 4 temperatures here, here and here and here. So, from these two I calculate the delta T across the length LA, I calculate delta T across length LB, and using the fact that the same amount of heat is transferred across the first the SRM as well as the sample, I can write Ka delta Ta by La. Delta Ta is measured by the two thermocouples, La is known. Similarly, is equal to Kb delta T by Lb, or we rearrange it such that I get Kb equal to Ka into delta Ta Lb divided by delta Tb La. So, all I have to do is to know the thermal conductivity of the material A, which is the standard reference material. Then I measure the two temperature differences and the two lengths, and I am able to estimate the thermal conductivity of the material whose thermal conductivity is unknown. So, a comparator, because we are comparing the performance of the two materials by imposing the same amount of heat transfer through each one of them. So, let us take an example which is actually taken from an experiment which has been performed in our laboratory. So, a thermal conductivity comparator uses a standard reference material whose thermal conductivity is known to be 45 plus or minus 2% watts per meter Kelvin. Two thermocouples, of course, you can see here that it is a high temperature, high thermal conductivity material we are talking about, and therefore, we will also have to use a relatively large length for the specimen to get adequate temperature drop. So, two thermocouples placed at 22 plus or minus 0.25, this point plus or minus 0.25 is the uncertainty in the location of the thermocouple, indicate a temperature difference of 2.5 plus or minus 0.2, again this is the uncertainty in the thermal temperature difference which is measured. The material of unknown thermal conductivity is in series with the SRM as indicated in the comparator and indicates a temperature difference of 7.3 plus or minus 0.2 Kelvin across the length of 20 plus or minus 0.25 millimeters. So, 22 and 20. So, determine thermal conductivity of sample and its uncertainty. All the assumptions you make, you must try to mention them, and we will of course work out the solution on the board. What are the assumptions we make? We already have discussed them. Is the same amount of heat transfer take place through the two of them, the SRM as well as the sample. That means there is no heat loss from the lateral direction. In fact, in this case the contact between the two of them need not be very perfect, because we are not measuring the overall, the heat transfer itself is not measured, the temperature difference is measured, the heat transfer itself we need not measure, therefore heat transfer rate is not measured. We are measuring only the temperature differences and the length. So, that is why it is a very interesting method, because the heat transfer itself is not measured, only the ratios are required. Delta Ta, delta Tb, La, Lb, these are the ratios. In fact, a comparator, any comparator for any property measurement will involve only the ratios. That is the basic idea. So, let us work out the problem on the board. So, this will be example 43. All I have to do is to use the expression I gave in the slide. So, I will just write down what are the quantities we know. La is 22 millimeters. If you want, you can keep all of them in millimeters, because we are going to only take ratios. If you want, you can convert it into meters, it is up to you, because only ratios are going to come, and only the value of K of the specimen, the standard reference material, if it is given in SI unit, the K determined here will also come out to be in SI units, because all others are ratios only. So, this is 22 millimeters, LB is 20 millimeters, Then we have Ka, which is 45 watts per meter degree Celsius. Delta Ta is measured as 2.5 degrees Celsius or Kelvin, it does not matter, temperature difference is the same. When you represent a temperature difference, it can be either Kelvin or degree Celsius. And we also have measured delta Tb for the second material is 7.3 Kelvin or degree Celsius. So all I have to do is to use the simple rule Ka delta Ta by La is equal to Kb delta Tb by Lb, or Kb is equal to Ka delta Ta Lb by delta Tb La. All I have to do is to substitute the values. So therefore Kb equal to 45 into 2.5 into Lb is 20 divided by 7.3 into 22. So this will give you a value of 14.01 watts per meter degree Celsius. It could have been easily visualized. The LA and LB are very close to each other, 20 millimeters and 22 millimeters, more or less equal, slightly different. Delta Ta is smaller than delta Tb. Therefore, we expect the temperature, the thermal conductivity of the second specimen to be lower than that of the standard reference material, which is very clear. Now all I have to do is to calculate the uncertainties. I have to use this expression. So we will go back here. Kb is equal to Ka multiplied by delta Ta by La multiplied by Lb divided by delta Tb. So all I have to do is to determine the error bar on this, or the uncertainty of Kb. Of course, I am assuming that Ka does not have any error, no error, or I think it is given with a 2% error. So let us use that value. So this has got 2% error. Delta Ta and delta Tb are both measured with delta T's have an error of 0.2 degrees plus or minus degrees Celsius, and La, Lb have errors of plus or minus 0.25. I am using the same units, so it does not matter, plus or minus 0.25 millimeters. So all I have to do is to calculate using the logarithmic differentiation method equal to plus or minus square root of delta Ka by Ka whole squared plus delta Ta by, I will say delta of delta Ta by delta Ta whole squared plus similar terms delta Lb by Lb whole squared plus same terms for involving delta Tb by Tb whole squared plus delta La by La whole squared. Due to the error in all the quantities, I will not substitute all the values and keep looking at it. I will just say that delta Kb by Kb or delta Kb equal to plus or minus Kb into this whole thing. If you substitute all the values, it comes to delta Kb comes to 1.24 watts per meter degree Celsius. So the uncertainty in the value, therefore you see that we can say that Kb equal to 14.01 plus or minus 1.24, so many watts per meter degree Celsius. That is the error bar in this particular problem. The error is quite something like about 9%, about roughly 9%. We can also discuss this error by looking at how we can reduce the error. For reducing the error, what are the sources of error? Sources of error, of course, the measured values. The Ka we have no control because Ka has got a specified value of 2%. It is the delta T's which need to be measured more precisely. If we can measure the temperature differences much better than 0.2 plus or minus 0.2, and also the locations of the thermocouples are more precisely known, I think we improve the accuracy of the measurement, precision of the measurement of the thermal conductivity of the material B. By suitable choice of various suitable improvement, if we can bring it down to about plus or minus 5%, that will be acceptable for most engineering applications. So with this, we have looked at basically the measurement of thermal conductivity by steady state methods. What I will do now is to look at the measurement using an unsteady method. A typical example I am taking is the laser flash apparatus. And what does the laser flash apparatus give me? Before I tell you what we are going to get, let us look at the apparatus and find out how it is arranged. I have got a sample here, thin slice of the material whose thermal diffusivity I want to measure or estimate, and it is in the form of a thin sample. One side it is going to be a certain amount of heat is going to be supplied by a laser or a flash, which is going to be for a very small length of time. In a microsecond or millisecond, the laser flash will illuminate this side, and the energy absorbed by the front surface will slowly diffuse through the material. So the energy is supplied to this side of the sample by a flash or a laser, which is going to be for a very brief period. Okay? And then at the back of the sample, I have attached a thermal temperature sensor. I am going to study the transient response of the temperature sensor applied at the back, and I will amplify the signal if necessary and record it. There is no need to measure the temperature accurately or to measure the temperature. Some effect of the thermocouple response without worrying about the units I can record, and this is enough for our purpose, as you will see in a little while from now. The sample thickness is the length L, and the sample material thermal diffusivity I am assuming is alpha, which is known to be, we already know that thermal diffusivity is nothing but the ratio of K divided by rho Cp, rho C. So thermal conductivity divided by the density specific heat product. So if I know the specific heat and the density of the material whose thermal diffusivity I am measuring here, I can, having measured the thermal diffusivity here, I have to multiply it by the product of density and the specific heat to get the thermal conductivity. So the laser flash apparatus is going to give me only the thermal diffusivity, and if I know the other thermal properties like the specific heat, which of course I am going to discuss a little later, and the density, I can estimate the thermal conductivity. So the method is very simple in terms of its application. I have a laser or a flash which goes for a very brief period, dumps a certain amount of energy onto the one side of the sample. The sample itself is surrounded by a furnace at a constant temperature. For example, if I want to measure the thermal diffusivity material as a function of temperature, all I have to do is to put this sample inside a furnace, bring it to the desired temperature, so that the sample as well as the furnace is at a equilibrium temperature which may be any value we want, and momentarily I am going to introduce a certain amount of heat on one side which may increase the temperature of that side by only a few degrees, 1 or 2 degrees above the equilibrium value. So, what I will do is I will just look at the amplified signal from the back of the sample, and the pattern of this is going to give me the thermal diffusivity, as you will see from the next slide. Before we do that, we will introduce two quantities. One is the non-dimensional time, or it is also referred to as the Fourier number, which is given by pi squared alpha thermal diffusivity multiplied by time divided by square of the length of the thickness of the sample, and the non-dimensional temperature I am going to define as the temperature divided by the maximum temperature recorded from the back surface of the sample. So, if I make a plot of the non-dimensional temperature ratio as a function of the non-dimensional time or the Fourier number, you get a unique curve which has got the property that at a value of non-dimensional time equal to 1.37, the value of the non-dimensional temperature ratio is exactly half. So, 1.37 equal to pi squared alpha t by L squared. So, all I have to do is find out the time at which this happens. You find out when the maximum the temperature is going to be equal to half the maximum temperature. Maximum is here, half the maximum is here. So, you find out from the actual measurement what is the time at which the temperature ratio is half. That should correspond to a non-dimensional time of 1.37, and therefore, you take pi squared alpha t which is measured divided by L squared, L is also known, is equal to 1.37. From this I will determine the alpha of the material, alpha equal to, so 1.37 equal to pi squared alpha t which is measured divided by L squared. So, I can determine the thermal diffusivity. The method is somewhat expensive, and that is the only major drawback of the method, because the laser and the temperature recorder and so on are expensive equipment, but it is a very accurate way of determining the thermal diffusivity of materials. So, with that we come to a close as far as the thermal conductivity related topics are concerned. Now, let us look at the measurement of the specific heat of a solid. So, I will describe only one experiment, and the idea with which I am going to describe the experiment is to indicate how the experiment is designed such that we can take into account the unknown things like heat loss during the experiment. It is estimated by a clever way of measuring the measurement. It is an estimation of the heat loss which is central to this particular measurement technique. So, the calorimeter is an instrument which is used whenever we want to make the measurement of specific heat or latent heat and such other quantities. Any heat capacity measurement requires a calorimeter. Calorimeter by definition involves the measurement of heat as a quantity which is going to be either going from one system to another system or redistribution of heat, and the idea is to measure this accurately and taking into account the losses which may be present in the system. Essentially, the calorimeter consists of an inner vessel which we call as the calorimeter, and the inner vessel consists of a thin walled vessel with a liquid, in this case it may be water or some oil, and the temperature of this oil or the water is measured very accurately using a precision thermometer as indicated here. And there is an arrangement by which we can drop the hot mass, which is whose thermal specific heat which we want to measure. It can be easily transferred or immediately transferred to the inside by a suitable arrangement for dropping it. And also we have a stirrer which maintains the uniform temperature in the or promotes the mixing in the vessel, in the calorimetric vessel, and we surround it by a second vessel by a water jacket which is maintained at a constant temperature, and the temperature is measured using this thermometer which is shown here. So, the experiment is very simple. You take a certain amount of the material, usually in the form of beads or pieces of the material whose thermal specific heat I want to measure, heat it separately in a different environment. For example, you can put the material inside a oven, bring it to the desired temperature, and immediately transfer it by dropping it to the calorimetric vessel, and immediately start after dropping, you start noting down the temperature as a function of time. So, from the time temperature graph, we will be able to estimate the specific heat of the material which has been dropped after being heated separately and then dropped. The initial temperature of the calorimeter as well as the water jacket will be the same. We can refer to as T1. The temperature of the mass which is being dropped can be taken as T3. Finally, the temperature of the calorimetric vessel goes to a value equal to T2. So, these are the temperatures which we are going to be interested in. So, once these temperatures have been measured, I can estimate the specific heat of the material. Before we go to the example, let us just look at the theoretical background required for explaining the material method. So, this is calorimetry. So, what are the things which happen? Let us look at the various features of this method. So, there are two parts to the experiment. One is the mixing process. I am talking about mixing in a thermal sense. So, hot mass, hot sample dropped into the calorimeter, so the temperature of the mass which is dropped is higher than the temperature of the medium, either oil or water taken inside the calorimeter, and therefore the temperature of the water will increase. We are talking about very small temperature increase. How do we guarantee this? We guarantee by taking a small amount of the material whose thermal conductivity is to be measured. We have a large thermal mass for the calorimeter. So, increase guaranteed by having a large thermal mass for the calorimeter. The thermal mass of the calorimeter is given by the mass of the material of the calorimeter, that is the water plus the walls of the vessel, and the specific heat of each one of these. You take the product of the mass and specific heat, that is the thermal mass of the system or the calorimeter. So, if you have a large enough value compared to the thermal mass of the drop mass which is going to be dropped into the calorimeter, if you guarantee that, you will have a small temperature rise. We want the temperature rise to be small, so that the losses will be also small. That is the reason why we want to have small temperature rise. In fact, from measurement of point of view of the temperature, a larger temperature difference would be, larger temperature change would be desirable, but if you want to have a larger temperature difference, the losses also will be larger. Therefore, the estimation of the losses becomes the major problem. So, you have a mixing process which consists of a hot sample which is dropped into the calorimeter. The calorimeter has got a thermal mass which is much larger than the thermal mass of the material which is being dumped into it. The second part consists of the cooling process. So, let me just describe what happens. I will make a simple sketch here. So, this is the time axis, the temperature. I have the calorimeter at a temperature T1, which is also the temperature of the jacket. This is also equal to jacket temperature. It is the same as the jacket temperature. So, let us draw a line like this. Now, during the mixing process, I am adding certain mass of material at a higher temperature into this material, into the calorimeter. Therefore, the temperature of the calorimeter will show an increase. So, let us just assume that it goes up like that. So, it will go up till it reaches some value, we will call it as T2 dash. And if there are no losses, this temperature will remain fixed at this value. This will be constant. If the losses are 0, there are no loss, so we will say no loss case. But what happens in real practice? There will always be some loss. Therefore, we expect the temperature to go like this, not to the full value, but to some value we will call it as T2, which is less than T2 prime. And if you allow it to, after the temperature, this is let us say during this is the mixing, this is the time for which mixing is taking place, maybe a few seconds, and then the temperature will come down like this. This is the with loss. So, if you have a loss, what will happen is that the temperature is going to be lower. So, we can say T2 is less than T2 prime, and with the loss the temperature is going to come down continuously, and after some time, of course, after long enough time, if you leave, it will come back to the room temperature or the jacket temperature. Okay, this temperature will come down. Of course, it cannot go below that, it will come to the jacket temperature because of the heat loss. That means, okay, during the heating process, during the mixing process, there is some heat loss. Therefore, this temperature did not reach that value. Of course, I am in this figure, it is very highly exaggerated. The temperature difference may be very small, and then it starts coming down instead of keeping constant. So, if you look at this, this is the error. Similarly, here, this is the error. So, if I want to calculate the specific heat accurately, I must account for this error and make it up. That means that I have to add this. This is due to heat loss. So, how am I going to account for it? Let us write the appropriate equation and it will become clear as to what is going on. During the mixing process, the amount of heat given up by the hot mass which is dropped into it. So, heat given up by hot mass is equal to heat gain by calorimeter plus loss. So, I can write the heat given up by the hot mass as the mass equal to mg specific heat product multiplied by T3 minus T2. T3 minus T2. It has come to the same temperature as that of the calorimeter at the end of the mixing process. The heat gained by the calorimeter is given by the thermal mass of the calorimeter, which I will call it as capital C, multiplied by T2 minus T1 plus I will say loss is capital L. So, this is the equation. I can actually I am measuring T2, I am measuring T3, I know mass of the solid which is transferred. I can actually use this expression to determine Cg as nothing but C into T2 minus T1 plus L divided by mg into T3 minus T2. So, the problem is, this is the problem, all these are measured and this has to be measured. So, how do we estimate L? How do we estimate L? We can make a suitable assumption for this, that the loss is, if you remember in the radial flow heat conduction apparatus, we saw that the loss is proportional to the delta T, the temperature difference between the inner cylinder and the outer cylinder. Therefore, I can assume here also that the loss must be proportional to the temperature of the calorimeter minus the jacket temperature. So, we know that it has to be determined by the difference in temperature between that, and therefore, we can assume that the loss is proportional to the temperature minus temperature T1. Actually, I can say that loss is proportional to equal to some K multiplied by T minus T1, and if I know what the value of K is, I will be able to actually determine the error or the loss, and then I will be able to determine the specific heat accurately. So, in the next lecture, I will complete this derivation of the required equations for this particular case, and then take up an example which will show how the specific heat of a material sample is determined by this method. Thank you.